Hello guys, welcome back to the CCNA routing and switching video series brought to you by ABY Design and Tech. In this video, we are going to take what we've learned from the previous videos about the OSI model, TCP, IP, Ethernet, and we're now going to apply this to a real world scenario to see just exactly how computers go through the OSI model to build that data, add the information to that data, so we can communicate from point A to point B. So before we get into it, let's set the stage, okay? So imagine that you are a help desk analyst called Bob, and you're tired of work on the help desk. You have aspirations to become a network engineer. So through whatever means, you find out about a new CCNA training series on YouTube by ABY Design and Tech. So the first thing you do, you open up your web browser, you type in youtube.com into the address bar, and you press enter. What happens next? Okay, so the first thing that happens is youtube.com. That is just the name of the server which is holding the YouTube webpage. It's like me saying that there's a party in my house, Abd's house. Now chances are that doesn't mean anything to you. If you actually wanted to know where my house was, you would have to find out my street address. In a similar fashion, computers or devices over a network communicate using IP addresses. The reason why we assign names like YouTube.com or Gold.com to servers, etc., is because they're easily recognizable and easily remembered by humans. What actually goes on in the background is that when you type in, or when Bob typed in YouTube.com into the web browser and press enter, your computer is going to generate a DNS request and send it to a DNS server. It's going to say, look, I want to find out the IP address for youtube.com, the IP address for the server called youtube.com that holds the YouTube homepage or the YouTube website. Once the server receives your DNS request, or Bob's DNS request, is going to respond back with a DNS response, essentially saying that youtube.com has got the IP address 216.58.204.238. That DNS request is received by the computer. Now, once the computer receives that DNS response, it's going to know the IP address of that server which holds the YouTube website. Now, before any data is sent, or before Bob requests that website from that youtube.com server, requests that web page, the first thing that happens is that Bob has to establish a TCP connection with the web server youtube.com. The reason why he needs to establish a TCP connection is because web communication with HTTP or HTTPS takes place over TCP port 443 or TCP port 80. Because it uses TCP requires a connection be established so that TCP can provide all the cool features it does, such as acknowledgement of packets, retransmission of lost data, etc. So Bob is going to initiate the TCP connection by sending a SYN message to the server, and the SYN message is going to have a sequence number of 0. Essentially, this TCP three-way handshake is to establish the TCP connection and to synchronize on both sides what sequence numbers they are going to be using for their data. So a SYN message is sent with a sequence number of 0. The server responds back with a SYN ACK message, which essentially the ACK, it lists a acknowledgement number of 1, saying that I have received your SYN message, and the first sequence number I am going to use, and then the first sequence number that I expect from you after this TCP connection is established is going to be 1. So I expect that the first data packet you send to me is going to have a TCP sequence number of 1. It then sends a SYN message of itself, again to denote to Bob's computer that this is the sequence message, this is the sequence number that I'm starting off with. Again, it's saying that I agree, I want to establish a TCP connection with you as well. Now, Bob is going to receive this SYN ACK message and going to respond with an ACK message back, saying that, okay, I've received your SYN message and I'm setting the acknowledgement number to 1 to acknowledge that I've received your SYN message, and the first TCP packet that you send to me should have a sequence number of 1. So now the TCP connection is set up and both sides have synchronized and initialized what sequence numbers they are going to begin with when they actually start to send and receive data. Now, once that's done, the operating system or the application on Bob's computer is going to move down from layer 7 through 5 to actually build the data that it's going to be sending. In this case, it's just going to be a HTTP GET request for the homepage of the youtube.com website. And so it's going to take So layer 7 is going to build that raw data, and then layer 6 is going to format that data into a format that HTTP or HTTPS understands. Now, once that data is built, so layers 7 through 5, they focus on building the data that we're going to send. Layers 4 through 2, they focus on adding additional information onto that data so that we can get the data from point A to point B and to the correct application or to the correct service. So layer 4 is about adding information onto the data to denote the sender application and the receiver application. So in this case, once the application has built that data, it's going to send that data down to TCP, to the TCP protocol. TCP is going to define the source port, so that's going to be the sending application, aka the web browser that Bob opened up to type in youtube.com, and it's going to find the destination port, in this case 443. The destination port is going to be the HTTPS service running on the web server. Now, HTTPS is similar to HTTP, but HTTPS defines how we can communicate web pages, etc., securely over a network. And it's going to set the sequence number to 1. So the sequence number identifies whereabouts we are in the overall data stream of data that we need to send. And so in this case, the server is expecting a sequence number of 1. And the reason why we give it a sequence number of 1 is because that's the sequence number assigned to the first byte of data in this TCP packet. Now, once TCP has finished adding the information that it needs to add on to the data, it's going to then pass that data down to the IP protocol. Now, the IP protocol, it defines the ultimate source and the ultimate destination, where we are going to end to end. So in this case, it defines the source IP address as being 200.1.1.10, the IP address of Bob's computer. It defines the destination IP address as being 216.58.204.238, the ultimate destination, the IP address of that server holding that YouTube website. And it's important to know that the IP header is added on to after the TCP header. So essentially, we have our data, we then add on a TCP header, then we add on a IP header. Once IP is done with all the end-to-end addressing, it then passes the information down, or the data down, to layer 2, which is going to be Ethernet. It's going to pass it down to the Ethernet protocol. Now, Ethernet defines where we are going to based on a node-by-node basis. Essentially, so think of it like this: IP defines where we're going to end-to-end. This is the initial source, and this is the final destination. Ethernet, or layer 2 protocols like Ethernet, they define where we need to send that data to next to get that data to the final destination. And so think of it from Bob's computer's point of view. Bob's computer knows that the IP address 216.58.204.238, that doesn't reside in the same network as me. So I don't have a direct connection to their web server. I need to go through another device in order to get one step closer to reaching that web server. So in this case, Bob's computer is being programmed to know that any device that I want to communicate with that doesn't reside in the same network as me, I need to send that data to my default router, to my default gateway, because it will know how to reach there. So in this case, it's going to add on an Ethernet header and trailer to that data. The Ethernet header is going to have a source MAC address of Bob's computer, so AAAA. The destination MAC address, where this packet needs to move to locally from this local perspective, is going to be Bob's default gateway, which has the MAC address BBBB. So essentially, what this is saying, to reach 216.58.204.238, I have to go through my default gateway. It's going to add on a Ethernet trailer, which is used to make sure that the frame hasn't become corrupted during transit, and then it's going to transmit that frame. So obviously, it's going to send that frame to a switch. The switch is going to look at the destination MAC address and realize that this frame is destined for the default gateway of this network. Is they're going to switch those packets from one interface, so switch those frames from one interface to another interface, and then send that frame over to the default router. The layer 1 is all about transmitting. They're putting the bits onto the wire and sending them out. So now, what does the router do once it receives that frame? The first thing it's going to do is look at the source and destination MAC address. It looks at the Ethernet header and trailer and realizes, wait a minute, this piece of data is destined for me because I can see my MAC address listed as the destination MAC address. Let me strip away or remove the Ethernet header and trailer and process this packet further. Then it looks at the IP header and realizes, wait a minute, this packet isn't actually destined for me. Whoever sent this packet, whoever sent this data, just wants to go through me to reach that final destination of 216.58.204.238. So now, what my job is? My job is to look at my routing table to find the best route to route this packet. So essentially, it looks at its routing table to find out where do I need to send this packet to next, so that I can get a one hop closer or one device closer to that final destination. In this case, it looks at its routing table and realizes that in order to move this packet closer towards the final towards the final destination of 216.58.204.238, I have to send this packet to a router with the IP address 216.58.204.1, because that router will know how to reach that final destination IP address. That router, my routing table is telling me that I need to send this packet to that device next to get one step closer to that final destination IP. So in this case, it's going to add on the Ethernet header and trailer. The Ethernet header is going to have the source MAC address of the router's MAC address, which is going to be BBBB, and it's going to have the destination MAC address of youtube.com's default router, which is going to be CCCC. And so the reason the source MAC and destination MAC are different, because you have to remember, is that layer 2 defines where data needs to travel to from each devices, from each local network's perspective. So in this case, the packet the frame is moving from the router in Bob's network to the router in the youtube.com's network. And it's important to know that in real life, again, I've just done this as for a learning example, but in real life, your router is not going to have a direct connection to the router for YouTube's network. Instead, you will probably have a direct connection with your ISP's router. You would send that traffic to your ISP, and then obviously it would go through multiple routers until it finally reaches that end destination. So the story repeats itself again. YouTube.com's default router is going to receive this Ethernet frame that was transmitted by Bob's router, is going to look at the layer 2 information, realize that this frame is destined for himself, so he's going to process that further, looks at the IP header and realize, wait a minute, this frame isn't actually meant for me. This frame is meant for the web server residing on the 216.58.204 network. So now I'm going to look at my op table. I'm going to look and build a new Ethernet header and trailer. In this case, I'm going to put the source MAC address as being my MAC address of CCCC. I'm going to put the destination MAC address of the web server, which holds the YouTube website, which in this case has the MAC address of DDDD. And then it takes that Ethernet frame and transmits that to the switch, which then switches that frame to the web server holding that YouTube website. Okay. Now, what does the server do once it receives that frame? Well, the first thing it's going to do is take away the Ethernet header and trailer. Essentially, it looks at the Ethernet header and realizes, wait a minute, this frame is destined for me, so let me just process this frame more. It then looks at the IP header and realizes, wait, this frame is actually destined for me, because I can see my IP address listed as the destination IP address, which means that this packet has made it to its final destination. The server then strips away the IP header to reveal the TCP header. Now, the TCP header defines, again, the sequence number. So obviously, the server just checks the sequence number to make sure that that's the sequence number that it was expecting of the next TCP packet. But most importantly, the TCP header is going to define the sender application and the receiver application. So to which application this server needs to send this data to so that it can be processed. In this case, it's going to have a destination port of 443, which is the well-known port used for HTTPS. It's then going to strip away that TCP header to just leave that data, and then it's going to forward that data over to the correct service, the correct application. In this case, it's going to be the HTTPS web service running on the server, who will then process that data. Once that data has been processed, it's going to then send that YouTube homepage to Bob, and then that's how we get the YouTube homepage displayed on our web browser. It's literally as simple as that. Now, I wanted to take a step back and essentially have a look at the data which is being sent. So it's important to understand that the size of a TCP segment or IP packet or Ethernet frame is defined by how much data we are actually sending. So in this case, a TCP segment is just going to be data plus the TCP header. So in this case, imagine that the HTTP GET request we're sending is 900 bytes. Okay, when that data is then passed down to TCP and TCP builds a TCP segment, the TCP segment is going to have a overall size of 920 bytes. It's going to be the original data plus the size of the TCP header added on. The average size of the TCP header is usually 20 bytes. An IP packet is going to be the data plus the size of the TCP header plus whatever the size is of the IP header. So in this case, the IP packet is going to be 940 bytes. The Ethernet frame is going to be the original data plus the TCP header plus the IP header plus the size of the Ethernet header and trailer added onto that. So in this case, it's going to be 958 bytes because the Ethernet header and trailer combined is going to be 18 bytes. So I made a bit of a mistake here. The Ethernet trailer isn't actually 8 bytes, that should say 4 bytes. So the combination of Ethernet header, which is 14 bytes, plus the Ethernet trailer, which is 4 bytes, should give us another 18 bytes of information to add on top of the IP header, which is going to give us with an Ethernet frame size of 958 bytes. So I thought I would mention this to you because it's important to understand that the size of IP packet or the size of Ethernet frame or TCP segment is essentially defined by how much data we have already encapsulated plus the size of adding the header for that layer on top of that data which is already encapsulated. And that's it to it. That's all there is to how computers actually use the OSI model in real life to send and receive data. So it's literally as simple as that, where we build our data from layer 7 through 5, we add the necessary information onto that data, and then we transmit it. And as you can see, by a hop basis, the only information that is going to change is going to be the layer 2 information, the Ethernet information, because that defines which is the next device in line that we need to send this data to get it to its final destination. The TCP header and the IP header, they remain attached to the data until it reaches a final destination. If you have enjoyed this content and would like to see more content like this, then please subscribe to my channel. If you found this useful, then please share with others so that we can get high quality IT training to the masses free of charge. Thank you very much.